Hello, and today I'll be covering how to program an EEPROM, specifically a 16K I2C serial EEPROM from Microchip, the 24LC16B. Now we're going to first go over the datasheet. In the main features, we have a minimum operating voltage of 1.8 volts, and then our current consumption when we're using the device is about 1 milliamps and 1 microamps in standby mode. This is useful for when you're running your project off of a battery. The memory inside the EEPROM is organized as 8 blocks of 256 bytes, which gives you this 8 times 256 times 8, which gives you the full 16 kilobits. It uses a 2-wire interface, or otherwise known as the I2C protocol. And in the 2-wire protocol, it can run from 100 kHz to 400 kHz. It has a page write buffer of up to 16 bytes. Write cycles to the EEPROM typically take 2 milliseconds. Hardware write protected, has about 1 million erase write cycles, and has data retention of more than 200 years, which is practically impossible to test. Now the chip is an electrically erasable PROM that refers to an old method that the previous PROMs used, where you use UV light to erase the PROMs, instead of being able to directly erase them from, say, a microcontroller or whatever interface you are using. Now again, the device is divided into 8 by 256 blocks. We have a page write of 16 kilobytes. Now the pin configuration is, for the device I am using, A0, 1 and 2 are completely disconnected and useless pins, while we have our ground as VSS, our positive voltage as VCC, then we have our write protect and our 2 interface lines for the clock and the data. And in the absolute maximum ratings, we can operate the device up to 6.5 volts, but it's recommended to use between 1.8 to 5.5 volts. Now as we go down, we get the functionality description, which just basically describes how the I2C protocol works. Then we go further down, we find the device addressing scheme on 3.6. This just describes how we access the blocks of memory. Now the most significant nibble of the address is always going to be 1010 binary. And then the least significant nibble is going to contain the address for the current block we are going to write to. And then the least significant bit going to tell the PROM if we are reading or writing to it, as described in this address breakdown, with this only being 7 most significant bits. Then we go further down, we have the write operation, which is described here, that we start with a start condition, and we write our device code, which is going to be the 1010 of the most significant bit, and then the block address that ranges from 0 to 7. And then lastly, the RW bit, which is going to be 0, as shown here, for a write. That will be the first bits we are going to write to it. Then we're going to follow it by the address which we want to start writing at. And then we're going to have an acknowledge bit. And then next one is going to be our data. And then lastly, we're going to send through a stop bit, shown here. First have our control byte, the address, which is the top 4 nibble. Then our block access, and our read-write bit over here. And then the address we want to write to. And then the data followed by a stop. Then we have a page write, which is effectively the same as a write operation, but instead of sending a stop after each data write, we continuously write for 16 bytes. Now something to take note of, if the master should transmit more than 16 bytes prior to generating a stop condition, the address counter will roll over and the previous data will be overwritten. So basically, you can only write up to 16 bytes at a time to the PROM. Otherwise, you're going to overwrite your data and write incorrect data to the EEPROM. Here's a functional description of how it's done. We send our start, we send our control byte, we send the starting address, and then we write until we have 16 bytes, and then we send a stop. You can opt to send a not acknowledge at the end, just to hang the bus so you can stop. Now I'm quickly going to give a visual breakdown of the internal workings of the EEPROM before we get to reading data from the EEPROM. Now we have our EEPROM here. Now each EEPROM contains 8 blocks of memory. Now these are addressed as 0, 1, 2, 3, and then all the way to 7. Now these blocks of memory contain 256 bytes. And then again, these 256 bytes are divided into 16-byte chunks. This is true for every block of memory. Now effectively what you have is you have an 8 by 16 by 16 blocks of memory. So in a single write you only be able to write here, and then here, and then here, and then here. So your addressing scheme will usually be 0, 16, 32, and then 48, and then 64. And this will continue on all the way to address 240, which will be the last page address you can write to. Now back to the datasheet. We have a look at the read operation. Now for the read operation, RW bit, the least significant bit, changes to 1 to perform a write to the EEPROM. Now when reading data, if you say you have written to a memory address, it auto increments the address by 1 automatically. So say you've written to address 0, then your next address that you will read will be address 1. So say if you want to read address 0 continuously, you need to continuously set it back to address 0. Now, random read just describes how to set up a specific read. I will describe it down below when we get to the timing diagrams. And then a sequential read, there's no restrictions like a page write. You can read the full 256 bytes at a time of a single block. If you need to read from different blocks, you are going to need to every time set the block you are reading from. Noise protection is irrelevant for now. Then we have a current address read description, which is not very useful. Then we have the random read, which we start with a start condition. We send a write command to the device. Then we send the address we wish to read from. Then we send a start condition again. And then we send a read control byte to the device. Then the device will stream the data. Then we do not send an acknowledge at the end. And then we send a stop condition. Now the sequential read will start exactly the same as the random read, but with the only difference is you send an acknowledge after every byte you have read from the device. Now the typical hardware connections you'll have is you'll have your SDA and SCL lines pulled up to your voltage supply with your SDA and SCL directly connected to some microcontroller talking to the device. And then your VP pin can either be pulled down to ground or to your voltage supply. But if it is pulled to your voltage supply, you will be unable to write to the device. And when it is pulled down to ground, it enables writing to the device. And let's go over some code for the EEPROM. Now typically what I would do is a structure looking like this, with the address being set to 1010 for a control byte, and then our block address set as 3 bits in our structure, and then the RW bit set as 1 byte in the structure. And just for reference, this is the name of the variable. Here I set the structure as 1A, which is the equivalent of the control byte. Then I set a pin on my micro as the WP pin to enable writes to the EEPROM, since I have a resistor that pull up on the WP pin. So by default it is disabled to write to. Then we go down. We set the write to 0 to enable write. I'm using this for loop to set the block number I want to write to. Then I do page writes to the EEPROM to fill the entire block with random numbers. So we start with a start condition here, and then we have our control byte over here that is set here and here, and then we tell it the starting address we want to write to. And then we write 16 data bytes to the PROM, and then we stop the line. And then we repeat this until we have filled the entire EEPROM. And here I do a sequential read from the EEPROM. Now the first thing what I do is I define my block again, which I'm going to loop through with the L. I set the RW bit as write. Then I do a start condition here. Then I write my control byte. Then I set the starting address I want to read from. Then I set my RW bit to a read. Then I send a repeated start condition through. Then I send the control byte for a read. Then I read 255 bytes from the buffer, which I send with an acknowledge through. On the 256 byte, I do an I2C read without an acknowledge, and then I send a stop through. And then I have some data validation over here, just to check if the data is correct in the EEPROM, and if not, switch on my LEDs and then wait. And that's a basic introduction to using an external EEPROM. Any code that I've written will be shared on my Git. A like, share, comment and subscription would be greatly appreciated. Thank you. Have a nice day.